video lecture on dynamics of machinery. In today's lecture, we'll discuss about next part involved in basic concept of vibration. So next part involves the following points such as classification of vibration, then degree of freedom, then steps involved in the vibration analysis. The classification of vibration. Vibration can be classified like this one: free vibration, then force vibration, undamped and damped. We'll see one by one. Free vibration: a system after an initial disturbance is left to vibrate on its own. The ensuing vibrations is free vibration. If you focus on the first diagram shown here, spring mass system, if the initial disturbance is given for this mass, okay, the system vibrate as it is because of its own elastic properties, okay, and what are the corresponding vibrations are nothing but the free vibrations. Now if you look towards the next one, force vibration. If a system is subjected to an external force, the resulting vibration is known as force vibration. If the system start vibrate under the action of some external force, okay, the vibration comes in the system because of application of some external disturbance, or the external force is continuously acting on the system so that the vibrations in the system comes. Okay, this is the case of free vibrations. Okay, free vibrations are here, okay, in front of you. So next one is nothing but the undamped and damped vibration. If no energy is lost or dissipated in friction or other resistance during the vibration is undamped vibration. Okay, if any energy is lost in this way, however, it is called damped vibration. Now if you look towards this diagram shown here, okay, so whatever the displacement of this one mass and this one spring takes place here, that can be indicated with the help of this black line here. Okay, so black signal, okay, is in front of you. At the same time, look towards this one blue signal also. So whatever the loss takes place during the motion, okay, maybe because of some energy loss, okay, so this is known as damped vibration, okay, and this is known as undamped vibration. Okay, so no energy loss takes place, that's why this signal we can get continuously or periodic. This is also known as periodic motion. Okay, so this case actually is shown here, amplitude versus time. Okay, so response curve of undamped free vibration, okay, comes like this one, periodic. And if you just see here, the response of damped free vibration, okay, here that response actually goes in reducing order. Okay, so this is the case of damped vibration. Next one is nothing but the linear and non-linear vibration. Now if you look towards this picture shown here, okay, so this picture is nothing but the basic parameters involved in the vibration system. So what are that basic parameters? Spring, mass and damper. So if all basic components of vibration behave linearly, the resulting vibration is linear vibration. If those behave non-linearly, the vibration is non-linear. Okay, so when this all the parameters, okay, behave linearly, then it is known as linear vibration. And when if those behave non-linearly, the vibration is non-linear. So what's about the next one? Deterministic vibration and random vibration. Deterministic vibration, value of magnitude of the excitation acting on the vibratory system is known. Okay, so if you look to us here, when we know the value of this force acting on any system, again if I consider the same system, okay, so if you know the magnitude of the force acting on this one, this is known as deterministic vibration. Value of magnitude of the excitation acting on the vibratory system is known, then this is known as deterministic vibration. So what's about the random vibration? The excitation is non-deterministic or random. The value of excitation at a given time cannot be predicted. Response of the system is also random. The statistical terms are required to describe the response. Now, if you look towards this one, so a random vibration, if you take the example of earthquake, so whatever the force comes from the bottom of earth and that passes over the other systems, if you take the example of buildings, then we cannot predict that force, magnitude of the force. Okay, that's why that force is also a random. At the same time, the response is also a random. So here, whatever the amplitude versus time or the force versus time, okay, a response shown, you can get that response like this one. Next one is nothing but the transverse vibration. Now say elements of a vibrating rod, beam, string move perpendicular to the axis. So this is the case of transverse vibration. Now what's about this one? Suppose if I consider the disc is attached at the end of this one beam. Okay, so all the particles of this one approximately moves perpendicular to this axis. The same case is here. Okay, see the transverse wave. Okay, so whatever this motion takes place in upward and downward direction. Okay, this is the case of transverse vibration. What's about the longitudinal vibration? Vibration along the direction of long axis of the rod. Okay, so if you just say whatever the vibrations of this one comes exactly parallel with that axis of a rod. Okay, this is known as longitudinal vibration or parallel vibration. The same case with the help of this one spring. Okay, so whatever the waves comes from this one, the exact actually comes parallel with each other. Okay, so this is the case related with the longitudinal vibration. So what's about the torsional vibration? Here, this is the case of torsional vibration. A periodic motion of shaft in which the shaft is twisted about its axis, first in one direction and then in other. This motion may be superimposed on rotational or other motion. If you look towards this one, disc, twisting and untwisting of this disc takes place continuously. This is the case of torsional vibration. This can be more clear to you with the help of this examples also. Lateral vibration. Lateral means here transverse vibration or perpendicular vibration. Longitudinal or axial or another name given for this one as parallel vibration. Okay, so see the direction, direction like this one, parallel direction. Here the perpendicular direction. And what's about the torsional case? If you look towards this one, whatever the disc is attached at the end of this shaft. Okay, so this disc is continuously rotate about this axis. So twisting and untwisting of this disc takes place. This is the case of torsional vibration. Now see degree of freedom. So what's about the degree of freedom? A system is said to be n degree of freedom of system if it need n independent coordinates to specify completely the configuration of the system at any instant. Now see the different examples shown here, the different types of these degrees of freedom. we have explained with the help of this some examples. Okay, so say the single degree of freedom system, then 2 degree of freedom system. Okay, so before moving towards the next point, just see the single degree of freedom system. As per we have discussed here, a system is said to be n degree of freedom system if it needs n independent coordinates to specify completely configuration of the system at any instant. Okay, now say how many coordinates are required for the movement of this spring mass system. Okay, so if you just see the constraints given for this mass in such a way that the mass will move either in upward direction or downward direction, means only one axis is required, axis, or here we can just say the motion is required for this spring mass system. Okay, linear motion is going on here. Okay, so what's about this one, the rotational motion? What's about this? This is nothing but a simple pendulum. Okay, simple pendulum is nothing but a heavy bob is attached at the end of inextensible string. Okay, when certain at some point when we stretch that bob towards one end and release it, this will start oscillate about its mean position. Okay, so how many parameters required to define its motion? So only one parameter here, so only one single angle theta is sufficient to define its motion. Okay, means here again one parameter is sufficient. Okay, so this is the case of single degree of freedom system. So what's about this is this case, just say what's about this example. This is nothing but a single slider crank mechanism. It consists of single here slider. Okay, then what's about this one, connecting rod, crank. Okay, whenever this one crank start its journey from this point to this one, the this one connecting rod push this one slider into this one forward direction. Okay, now say this actually required as only a single parameter to define its journey, here theta or here x. Okay, only a single parameter is sufficient to define its degree of movement. Okay, so this case comes under the single degree of freedom system. So what's about the next one, 2 degree of freedom system? So 2 degree of freedom system, a spring supported by a rigid mass, spring supported by or you can just say the two springs supported by a single mass, or two springs supported by the two masses are separate. Okay, so one mass is attached at the end of one spring, and towards the another side of that mass one more spring mass system is attached. Now see here how many parameters with us, the stiffness for this spring with us k1, stiffness for this one is k2 with us. Now whatever the mass is kept on the top surface of this one, top of this one, both the springs. Okay, the tendency of this mass to move in downward direction, means one axis is required here. And if you just say if I push this one mass in downward direction, okay, so here the theta parameter is required, means the two different parameters are required to define its motion. So this is the case of 2 degree of freedom system. Similar case is here. Here x1 and x2 parameter is required because the stiffness of this spring and this spring is different one. So you can get the displacement of the particular this mass different one, and for this mass you can get the different one. Now the next case is nothing but the double pendulum. So what's about this one? This is the simple pendulum. Okay, another pendulum is attached with this one. So if we pull whole system here, then whatever the angle made by the first pendulum with the this one mean position, okay, vertical position, is nothing but theta 1, and here theta 2, means the two different actually motions are required here to define its journey. So this comes under the 2 degree of freedom system. So next case is nothing but the 3 degree of freedom system. So three springs available with us here. Okay, because of the here we get the one rotational motion. Okay, so this spring is connected with this spring with the help of the string wound around on the surface of this pulley. Okay, so this actually pulley moves. Okay, means you can get one parameter, that is theta, and another one here x1 and x2, means three different parameters are required to define its journey. Okay, similar case with this one here, x1, x2, x3, because of the three masses involved in the system and the three different springs are connected. So this is the case of 3 degree of freedom system. Next one is nothing but the very interesting example, 6 degree of freedom system. So if I put any object in a space, it possesses the 6 degree of freedom, or it required the six motions, six different actually motions we can get along the three axis. Okay, now if you look towards this one, x-axis with us here, y-axis is here, the next one z-axis is here. Now try to just focus on this one, various actually pictures shown here. Okay, so here along the y-axis, the tendency of this man or this one, this will moves its head above of the shoulder. Okay, okay, like this one in rotational way. Okay, so one rotational motion passes along this one y-axis. Similar case here about the x-axis, this will actually rotate. About z-axis, this will also rotate, means three rotational motion along every axis. And if you look to us here, y-axis, okay, here upward motion and downward direction, here the movement along the this one x-axis translatory motion, then along the z-axis translatory motion, means three translatory motion along the three axis and three rotational motion along the three axis. Okay, this is the case of 6 degree of freedom. Then what's about the next one, infinite number of degree of freedom system. So next one is nothing but some systems, especially those having the continuous elastic members, have an infinite number of degree of freedom. Okay, this can be shown with the help of this one cantilever beam. And what's about this one, a flexible beam between the two support has an infinite number of degree of freedom. For that, if I just focus on this cantilever beam, if the displacement is given for this beam at its end, okay, now say the displacement of every particle available on this cantilever beam, okay, move by a different actually distance. Okay, if you focus on this particle, this one, this one, this one, this one, so if you look towards this one, we can get the x1 displacement for this particular particle, x2, x3, x4, okay, and onwards. Okay, so infinite number of displacement we can get for the infinite number of the particles available here. So what's about this one? This is the case of flexible beam when fixed between the two ends. Okay, now if you look towards this one, whenever the motion is given randomly, then whatever the waves comes inside of that one, means the displacement of every particle is a different one. So if you look towards this one, the displacement of that flexible beam between the two support, we can get a different one. Then we'll say the vibration analysis procedure. The vibratory system is a dynamic system for which variables such as the excitations, that is inputs, and response, that is the output, are the time dependent. The response of the vibrating system generally depends upon the initial conditions as well as the external excitations. You say, what are the different steps involved in the vibration analysis? So first step is nothing but the mathematical modeling. Okay, now say the purpose of mathematical modeling is to represent all the important features of the system for the purpose of deriving the mathematical or analytical equations governing the system behavior. Okay, then next step, before that step, just say the mathematical model may be linear or non-linear depending upon the behavior of systems component. Okay, then next step is nothing but the derivation of governing equation. Once the mathematical model is available, we use the principles of dynamics and derive the equations that describe the vibration of the system. The equations of the motion can be derived conveniently by drawing the free body diagrams of all the masses involved. Okay, so we know the different methods are there for the formulations of differential equations. That is, method based upon the free body diagram can be divided into two different types. First one, Newton's, are based upon the Newton's second law of motion, and second one based upon the D'Alembert's principle. Now next method is nothing but the energy method. Energy method is also classified into two different types. First one is nothing but the method based upon the release, and second one energy method. Both the methods actually depends upon the law of conservation of energy principle. So next one is nothing but the solution of the governing equation. So once the mathematical modeling step is over, next derivation of the governing equations with the help of various methods when we get. Okay, the next one is nothing but the solution of the governing equation. The equations of the motion must be solved to find the response of the vibrating system. Depending upon the nature of the problem, we can use one of the following techniques for finding the solution. Standard methods of solving differential equations such as Laplace transform methods, then matrix methods, and numerical methods. Last step is nothing but the interpretation of results. The solution of the governing equations gives the displacement, velocity, and acceleration of the various masses of the system. The result must be interpreted with a clear view of the purpose of the analysis and the possible design implications of results. Now, let us say how any physical system is converted into mathematical model by considering the basic parameters involved in the vibration study. Okay, for that, just see the modeling of forging hammer. So this system consists of a frame, a falling weight known as a tub, and anvil, the foundation block. The anvil is this one. This anvil is a massive steel block on which the material is forged into desired shape by the repeated blows of this tub. The anvil is usually mounted on elastic pad to reduce the transmission of vibration to the foundation block and the frame. For first approximation, the frame, this frame, anvil, and elastic pad, foundation block, and soil are modeled as a single degree of freedom system. Okay, like this one. Now look towards this picture carefully. Here So whatever this one anvil, this one foundation block, okay, we're just considering this foundation block anvil is unit system, okay, for the first approximation, okay. Now here whole this system is mounted on the this one foundation block, and below this foundation block the soil is there. So whatever the resistance comes from this soil in terms of damping, as well as whatever the stiffness possessed by that soil, we can just represent that stiffness and resistance comes for the motion of uh, entire system in downward direction, okay. So we can just show that with the help of this one damping, okay. Damper, one damper is shown here. So whatever the resistance comes from for that motion, we can just represent with the help of this damper. And whatever the stiffness, or elasticity term possessed by that soil, we can just represent with the help of this one soil stiffness. So mass term is here. Mass term we can just consider with the help of this anvil as well as foundation block, okay. So whatever the weight is falling in downward direction, just say that weight is nothing but here tub. So this is nothing but the mathematical model of the forging hammer by considering just approximate terms, okay. Now in a redefining case, if I separate this anvil and foundation block, if I separate this anvil and foundation block, in between this anvil and foundation block, elastic pad is provided, okay. So whatever the elasticity possessed by that block, we can just show that by spring stiffness, okay. So we can just represent that with the help of one spring, and whatever the damping properties provided by that elastic pad, we can just show by one damper. At the same time, this foundation block is mounted on this soil, okay. Below this foundation block a soil is there. So damping provided by that soil, we can just show with the help of this damper. And from another side, whatever the stiffness possessed by that soil, we can just show with the help of this spring, okay. Stiffness of the soil can be indicated with the help of this spring, okay. So here we are separating this one anvil and a block with the help of this elastic pad, okay. Now we can just show this anvil separately here, okay. And whatever the tub is falling on that anvil to give the shape for that particular component, okay. Now this is nothing but the refined actually model of this one mathematical model of this forging hammer. So again we can just uh, redefine various terms, okay, and we can get the final things, okay. In this way we can transfer this physical system into mathematical model like this one. So next case is nothing but the motorcycle with a rider, a physical system and mathematical model. For that, now next example, this one motorcycle with a rider, a physical system and mathematical model, okay. For that, now say here a rider riding this one uh, vehicle, okay. So what are the different points involved in this motorcycle? Here the stud with us, okay. Here the wheel, okay. Wheel is here, okay. So what's about this one? This indicate the tire, okay. Stud again here, okay. Now as initial approximation, whatever the equivalent stiffness and whatever the equivalent damping constant here provided by, so what's about this one? Tire comes directly in contact with this one road surface. So this equivalent part is nothing but whatever the mass we have considered here for the rider as well as the mass of this vehicle is nothing but the equivalent mass. So equivalent stiffness is nothing but, if I consider the various things involved in the picture, here the stud with us, then here wheel with us, here tire with us. Okay, so whatever the stiffness provided by all these parts are nothing but the here that K term indicate K equivalent is nothing but the equivalent stiffness of all this stiffness terms available in the system. So what's about this one? C indicate the damping coefficient, equivalent damping coefficient of all the resistances comes in the motion. Okay, so C indicate the C equivalent indicate the equivalent damping coefficient. Now this is nothing but the initial approximation where we can provide just consider only spring mass and damper system. So in the next stage, if I separate if I consider the mass of this vehicle separate, mass of this, okay, this one, mass of this rider, okay, this term comes into picture like this one, mass of the vehicle plus mass of rider. If I consider the mass of this wheel separate, okay, so one wheel is provided here towards the front side, on the back side another wheel is provided. Okay, so if I consider this one mass of the back wheel or rear wheel, here the front wheel with us, the mass for the front wheel we can just indicate by mw. So what's about this one? So whatever the stiffness provided by this stud, okay, we can get like this one ks. So what's about the this one? So damping is provided by this one, we can get in terms of cs, means one spring and one damper is provided here for the back wheel. Okay, that actually connected with the help of this stud. Okay, so similar case with the this one front wheel also, we can just show the damping provided by this stud with the help of this one cs. Okay, and whatever the stiffness provided by that stud is nothing but ks. So what's about next one? So kt, okay, kt, and this one whatever the tire available outside of this wheel, so whatever the stiffness provided by that tire we can just show in this way, kt for the rear wheel and kt for the this one front wheel. Okay, just only approximately you can this model is drawn here. Okay, now if we look towards next one, again if I redefine this model by considering the separate mass of the rider here, separate mass of the vehicle, then we need to consider whatever the this one stiffness provided by the this one stiffness stiffness comes from that rider itself. Okay, you can just get this one k r, okay, and cr terms here into picture. Okay, now if you look towards this one, the same term will remain here, same term will remain here. Okay, in this way we can just expand the model as well as we can reduce the model. So whenever actually expansion of this model takes place, okay, so depends upon the connections of the spring, whether that springs are connected in the series or parallel. Okay, depends upon that we can again get the equivalent stiffness of the springs here. Okay, similarly the damper provided here we can get the equivalent damping coefficients of the all the dampers. Similar case with this one, similar case with, okay, this one bottom springs are here, the two springs are connected here parallel, means here the two kt is written here, that's why here the two springs are connected in the parallel, that's why the 2ks is written. Similarly case with this one, two stiffness, sorry, two dampers are provided in the parallel, so here 2cs is written. So whatever the mass of the vehicle as well as the mass of the rider is considered here combined, so that's why the single mass is shown here, the two masses, here these two masses are added here. Okay, this is the next actually stage where we can get again redefined or final model of the motorcycle or mathematical model for that motorcycle. I hope concept we have seen in the today's lecture are clear to you. Thank you.